Hi, my name is Pragya Sethi and I'll be presenting our work called KG-QIF, a framework to improve the quality of knowledge graphs. A lot of factual information about different real-world entities and the relationships with one another is present on the internet in the form of product descriptions, Wikipedia articles, blogs, etc. These are usually in the form of natural English language. We need to convert this data into a structured format to be able to use it in different applications and downstream tasks like semantic search and recommender systems. Therefore, there has been extensive research in building knowledge graphs where such information is captured in a structured format in the form of triples that consist of two entities that are connected to one another by a relation. Existing techniques for converting natural language text to knowledge graph triples generate a lot of implausible triples. The entities and relations in these implausible triples do not link properly to open knowledge graphs like Wikipedia and Wikidata. To overcome this problem, we present our work called KG-QIF, that stands for Knowledge Graph Quality Improvement Framework, that both detects and improves or deletes implausible triples. In our method, we take two inputs. These two inputs include the triple that is generated by the user from existing tools like Ollie, OpenIE, and Plumber, and the source sentences from which the triples were created. Then we identify the possible errors in the triples and propose a modified triple. The entities and relations in these modified triples are passed on to linkers like DBpedia, Spotlight, and Falcon that further link them to DBpedia or Wikidata knowledge graphs. We divide the implausible triples into four categories: failed coreference resolution, imperatives, redundant triples, and uninformative triples. The failed coreference resolution triples are the ones that contain pronouns like he or demonstrative determiners like there, which don't really refer to any named entity. For example, in he worked as fighter pilot, the triple on its own cannot tell who he is referred to. Imperatives are the class of triples that are generated from imperative sentences that include orders, requests, etc. They don't add any factual information to the knowledge graph. For example, the instance click close to exit customer view does not add any factual information without knowing the context from which it is generated. Redundant triples are the ones that repeat the information that is already present in the knowledge graph. For example, the information that Johnny Blaha was born in San Antonio is covered in both the shown triples, and therefore the first triple is redundant. The category uninformative relations include the triples whose relations do not contain meaningful key phrases that can be used to link them to corresponding relations in open knowledge graphs. For example, is and falls under in the two triples that are shown on the screen do not include any key phrases that can be linked to corresponding DBpedia and Wikidata entities. So we employ multiple techniques to improve the triple quality. For example, in case of failed coreference resolution, we apply different coreference resolution techniques and choose the one which replaces the maximum number of pronouns and demonstrative determiners with their corresponding entities. In case of imperatives, we simply remove the triples since they don't add any factual information. In case of redundant information, we only keep the triples. We remove the triples that repeat any information that is already included in the knowledge graph. In case of uninformative relations, there can be multiple cases and we handle them differently. For example, if the word is a generated relation in the triple is or are, we convert it to type of to match it with the triple in DBpedia. So apple is a fruit is converted to apple type of fruit. In case of has, have, had, we check the sentiment of the object entity. If the sentiment is positive or neutral, we convert it to has feature. For example, Ganges has religious importance is converted to Ganges has feature religious importance. And in case the sentiment of the object is negative, we convert it into has problem. So Ganges has polluted water is converted to Ganges has problem polluted waters. In case the entire noun phrase of the verb's subject is not present in the relation of the generated triple, in that case we add the noun phrase. To detect the noun phrase, we use pause tagging and dependency parser. So if the original triple was 103 Kolmoguru falls under brutalist architecture, we find the noun phrase that falls under refers to, which in this case is the architecture style of 103 Kolmoguru. So we replace it with falls under the architecture style in our improved triple. And we see that while the original triple, in case of the original linked triple, we get none of the DBpedia relations is properly mapped to our generated relation. In case of the improved triple, the relation is correctly mapped to the correct DBpedia relation. The results of our experiments on WebNLG dataset are shown as follows. For table 3, we can observe that after applying our framework, there has been approximately 4 to 5% increase in the total number of predicates linked. From table 2, we observe that on applying our framework, the precision improves for both triple extraction modules, Ollie and Plumber, which shows that our algorithm returns more correctly linked triples than incorrect ones. However, the recall has become lower after applying our framework. This shows that our algorithm returns lesser number of correctly linked triples in total. This can be attributed to some of our techniques in which we simply remove the implausible triples instead of improving them. In future, we will work towards improving such triples using context from their source sentences by building some learnable techniques. Thank you.